As we continue our journey into CMOS logic design, today's focus will be on complex CMOS logic gates, specifically the AOR and OAI structures. Up until now, we have seen how simple logic gates like NAND, NOR, and inverters form the building blocks of digital systems. But when we move towards practical and large-scale VLSI design, efficiency in terms of area, speed, and power becomes crucial. AO and OI gates are powerful because they allow us to directly implement Boolean functions in sum-of products or product-of-sums forms within a single logic stage, eliminating the need for cascaded gate structures. This not only makes the logic faster but also significantly reduces parasitic effects and silicon area. Building upon our understanding of basic combinational logic implementation in CMOS, we now move into a more generalized class of complex CMOS gates. Among the many possible topologies to stand out as highly practical, the AND-OR-Invert AOR gates and the OR-AND-Invert OAI gates. These are not just theoretical constructs, but real gates included in standard cell libraries because they allow direct implementation of Boolean functions in either SOP or POS forms. Their biggest advantage is the ability to collapse multi-level Boolean logic into a single stage, improving both speed and area efficiency. The AOR gate is based on the sum of products logic form. Imagine we have multiple product terms like AB, CD, EF. These are realized as series-connected nMOS branches. These series branches are then connected in parallel to perform the OR operation. Finally, the entire network is inverted at the output. The PMOS pull-up is the dual structure of the nMOS pull-down, meaning every series path in nMOS becomes a parallel path in PMOS and vice versa. Hence, AOR gates are extremely efficient at directly implementing SOP Boolean forms such as F is equal to complement of A plus CD. To illustrate, let us take an AO22 gate, which implements the function F is equal to complement of A dot B plus C dot D. In the pull-down network, we create two parallel branches. In the first branch, nMOS A and nMOS B are in series, and in the second branch, nMOS C and nMOS D are in series. This structure gives us A plus CD in the PDN. The PMOS pull-up network is simply the dual graph, so A and B appear in parallel, connected in series with C and D in parallel. This duality guarantees correct complementary switching. Now, in contrast, the OAI gate is optimized for the product-of-sums form. Instead of product terms being OR-AND, here we have some terms that are AND together and then inverted. Structurally, this means the nMOS pull-down is arranged as series branches of parallel transistors. Each parallel pair represents a sum term like A plus B, and then multiple such terms are cascaded in series. Again, the PMOS pull-up network is formed using the dual relationship, ensuring complementary CMOS operation. A typical output would be of the form F is equal to complement of A plus B dot C plus D dot. As an example, consider the OI22 gate which implements F is equal to complement of A plus B dot C plus D or Z. Here, in the pull-down, A and B are in parallel, forming the A plus B branch, and C and D are also in parallel, forming C plus D. These two branches are then placed in series, which corresponds to the ANDing of some terms. The PMOS pull-up is once again the dual, where A and B appear in series and C and D in series, with the two series paths connected in parallel. Notice how efficiently the OI22 gate captures a product-of-sums expression directly. The power of AO and OAI gates lies in their efficiency. Since many Boolean equations can be expressed in SOP or POS form, these gates allow us to implement the function in a single logic stage. This reduces the logic depth compared to cascading NANDs or NORs, which not only makes the circuit faster but also reduces dynamic power due to fewer transitions across multiple stages. Additionally, compact layouts and fewer diffusion breaks make them silicon efficient with reduced parasitic capacitance. Because of these advantages, AO and OAI gates are standard components in our 6-cell libraries and digital synthesis tools. To summarize, The AOR gate directly maps to the sum of products form, while the OI gate corresponds to the product of sums form. In both cases, the NMOS pull-down network is structured according to the Boolean function, and a PMOS pull-up is simply the dual graph of that arrangement. Together, AOR and OI gates provide us with highly optimized ways to realize complex Boolean logic, offering significant advantages in speed, area, and power efficiency compared to using only basic NAND or NOR implementations. Having explored AOR and OI gates, which optimize logic realization, we now encounter another design challenge: the sheer transistor count and silicon area when implementing large functions in CMOS. Remember, in a full CMOS gate, every input bit needs both an NMOS in the pull-down and a PMOS in the pull-up. For complex gates, this quickly scales to a large transistor budget and consumes significant area. In high-density VLSI, where millions of gates are integrated, such redundancy becomes a limiting factor. To overcome this, designers introduced an elegant simplification known as Pseudo-nMOS, where the pull-up network is reduced to its bare minimum. In Pseudo-nMOS logic, instead of a full complementary pull-up network, we use just one PMOS transistor permanently on because its gate is grounded. This PMOS acts as a weak pull-up, supplying current to maintain the logic high state. The actual Boolean function is realized entirely by the NMOS pull-down network. If the pull-down path is active, it overpowers the weak pull-up, pulling the output low. If it is inactive, the PMOS pulls the node high. Conceptually, this is very similar to depletion load NMOS logic from earlier technologies, but adapted within CMOS fabrication. One of the biggest advantages of Pseudo-nMOS logic is the significant reduction in transistor count. By eliminating the complex pull-up network, the gate consumes much less area. This reduction also means fewer parasitics, which translates to faster evaluation times since the load on the output is lighter. Such a feature was particularly valuable in early dense circuits, such as memory arrays or arithmetic blocks, where maximizing gate density and speed was more critical than achieving zero static power. Of course, the simplification comes with clear trade-offs. Since the PMOS is always conducting, whenever the output is at logic low, a direct current path exists from VDD to ground. This results in static power dissipation, which full CMOS logic avoids. Another limitation is that the output low level, wall, is not ideal. It depends on the ratio of the PMOS load strength relative to the NMOS pull-down network. This makes noise margins smaller and signal levels less robust compared to standard CMOS. Thus, careful transistor sizing is required to balance functionality and reliability. To see this concept in action, consider the Pseudo-nMOS version of the OAI gate we discussed earlier. The pull-up is now just one always-on PMOS device, while the pull-down is the NMOS network configured for the OI logic function. This compact structure drastically cuts the transistor count compared to a full CMOS OAI implementation. Although static power is consumed, the design achieves better area efficiency and faster switching. Such implementations were historically popular in shrum bit cell peripheries and other high-density blocks where minimizing transistor count was essential.